so welcome back to my channel. Okay, so we're going to continue our lesson with buffer solution. Okay, I believe you already understand about salt hydrolysis, because only after understand about salt hydrolysis you can focusing on buffer solution. So this is my fourth video for our chapter 7. Okay, so by the end of this lessons video, you're going to understand about what is the buffer solution. Okay, so how does a buffer solution has the ability to maintain its pH after addition of small amount of strong acid or strong base, and using the Henderson-Hasselbalch equation, which is a special equation to calculate the pH of the buffer solution and its pH changes. Alright, okay, so let's now understand what is buffer solution. So buffer solution is a solution that has the ability to maintain its pH even you add a small amount of strong acid or strong base. So what does make a buffer solution? So buffer solution is actually a mixture of weak acid or weak base with its salts containing is either conjugate base or conjugate acid. So we have two types of buffer solution, which is the first one is your acidic buffer and the second one is your basic buffer. So both of these buffer solution has its own way on how to maintain its pH, which I'm going to explain further when we go through each one of these individually. Okay, so let's now talk about acidic buffer. Okay, so your acidic buffer, the terms acidic means it's made up of acid with its opposite component is the conjugate base. So okay, so your acidic buffer must have a pH less than 7. It's made up of weak acid and salts of its conjugate base. So I'm giving these first examples, which is your ethanoic acid and potassium ethanoate. Okay, I just want to highlight to you, okay, any buffer solution, they needs to have common ions between them for them to work as a buffer solution. For example, in this example, I have ethanoic acid and potassium ethanoate. So my common ions is this, which is your CH3COO negative, which is your ethanoate ion. Okay, so ethanoate ion present in both of my weak acid and my salt, so therefore they can work together as a buffer solution. Alright, so if there is no common ion between these two, no buffer solution can be produced. It will just be just a mixture of between two different compounds, but not a buffer solution. Okay, so the key here for systems to work as a buffer solution, they must have common ion between that weak acid or weak base and its salt. Okay, so our components of buffer systems, we need to divide into two. One is for our weak acid. Okay, this one is acidic buffer, so one is our weak acid and another one is our salts. Okay, so as we know, okay, so weak acid, weak means it's only partially dissociates in water. So partially dissociates in water, it will produce this CH3COO negative, which we label it as conjugate base. And H3O plus is the product of hydrolysis of our ethanoic acid. Okay, so it's partially dissociates, therefore you're going to see this reversible arrow. Okay, whereas the salts of potassium ethanoate, which is your CH3COO, okay, so any salts will undergo complete hydrolysis or complete dissociation to break down into its ions component, which we have this conjugate base, and K plus comes from a strong base KOH, therefore this one we label it as cation ion. So the common ions between them is CH3COO negative. Okay, so the common ion between them will work as the acidic buffer. So how does this mixture of ethanoic acid and potassium ethanoate control its pH? Okay, so this is it. Okay, after additions of small amount of strong acid, H3O plus, okay, it's just small amount of strong acid. Okay, so this H3O plus will be neutralized by, okay, so we have two components that make up our buffer solution in this one, acidic buffer. So we have weak acid or conjugate base. So one of these will neutralize its opposite component. So if it's a weak acid, it will neutralize base. Okay, whereas my conjugate base will neutralize any acid added to it. Okay, acid. Alright, so the first one, we're adding strong acid. So any acid contains H3O+. So it will be neutralized by the opposite component of it, which is base. And our which is the opposite component of it is our base. And in this one, we have the conjugate base, which is CH3COO negative. Okay, so write down the chemical equation involving the conjugate base. Okay, so the conjugate base will neutralize our added H3O+ from the strong acid. So it will become the CH3COOH, which is our weak acid plus water. Okay, so we can see that we are using our conjugate base, whereas we are producing our weak acid in the reaction. So it's the concentration of a weak acid. Okay, so the concentration of our weak acid increase a little, okay, due to the neutralization reaction that takes place between our conjugate base with the acid added. But, okay, just to remind you, this CH3COOH, your ethanoic acid, is a very weak acid. So it will hardly dissociate in water. Therefore, there will be no adding pH, there will be no added H3O+ into the solution. Therefore, the pH of the solution remains unchanged or remains unaffected. Maybe there will be a slight changes, but only very little change in the value of your pH, because of ethanoic acid is a very weak acid, which its dissociation reaction of your weak acid into water hardly to happen. Okay, whereas if you're adding your strong base OH negative, okay, so the strong base OH negative definitely will be neutralized by an acid, and our buffer, we have this ethanoic acid. Okay, so this ethanoic acid will react with the hydroxide ion added from the strong base to form our conjugate base plus water. Okay, so according to this dissociation equation of our ethanoic acid in the water, okay, so it's a reversible reaction, so it lies in equilibrium. Okay, so the added hydroxide ion will be neutralized by weak acid, thus our weak acid concentration will decrease, but we're producing more of our conjugate base. Okay, so if you can see in the hydrolysis equation here, so weak acid is our reactants and our conjugate base is our product. So higher concentrations of our conjugate base, which is on the right, will push the chemical equilibrium from right to left. So POE shift from right to left, resulting in we reproducing the ethanoic acid that we used before to neutralize the added OH negative. So as a result, okay, even though we use up our ethanoic acid first initially to react with our hydroxide ion added, okay, for the neutralization reaction, but okay, the conjugate base that we produce push, okay, since the concentrations of our conjugate base is increasing, so it pushed the chemical equilibrium of this reaction, reversible reaction, to the left, resulting in we reproducing back our ethanoic acid. So there will be no changes in the concentrations of ethanoic acid or ethanoic ion, resulting in no change in the pH of our buffer. Alright, okay. So let's look at the second example. Okay, so we are dissolving a sodium nitrite with nitrous acid. So another example for your acidic buffer. So let's learn how to explain how does this buffer system works to maintain its pH even after additions of small amount of acid or base, provided it must be strong acid or strong base is added into the buffer system. Okay, so we have to first to identify which one is our weak acid. So our weak acid is HNO2. Okay, so write down the hydrolysis equations of our weak acid in water, which is partially dissociates because it's weak acid, so reversible arrow. So that means reversible reaction. So we're going to produce H3O plus equals plus NO2 minus equals. Okay. And then we're going to write down the dissociation equation for our salts, which is a complete dissociation. So NaNO2 equals, okay, complete. So that means we use a single double-headed arrow. Okay, so going to produce Na plus equals plus NO2 minus equals. Okay, so as you can see, there are NO2 minus at both equation. So that means that is the common ions, NO2 minus. So therefore, this sodium nitrite and nitrous acid mixture can work as a buffer system. Okay, so what will happen if I add a small amount of strong acid? Okay, so our buffer component is made up of our weak acid, HNO2. So weak acid will neutralize OH minus, okay, because it's a base, whereas our conjugate base NO2 minus will neutralize any H3O plus is present. Okay, so additions of strong acid will strong acid of our HCl means it will have H3O plus, and as we labeled before, this H3O plus will be neutralized by NO2 minus. Okay, so let's write down the neutralization reaction equation between H3O plus, okay, with our conjugate base NO2 minus equals. So this one is a complete reaction. Okay, so it's going to produce our weak acid HNO2 equals plus H2O water in the liquid. Okay, so from the neutralization reaction, we are using our conjugate base. So concentrations of NO2 minus decreases, okay, but the concentration of our HNO2 increases. However, even though the concentrations of HNO2 is increasing, okay, because the pH of the buffer solution depends on the pH, depends on the concentration of these both, but HNO2 is a weak acid which hardly dissociates in water. Therefore, the pH of the buffer doesn't change very much. Okay, just a little. Alright. Never mind. I'm going to show you how do we calculate the pH of the buffer towards the end of this video. So you can see how the pH changes even after small amount of acid is added or small amount of bases is added into your buffer system. Okay, you will just see a very slight changes. Okay, right. So what about if I add a small amount of my strong base, which is NaOH? So any bases added means we have OH minus. So OH minus, so will be neutralized by the opposite component of it, which is acid. So let's write down the neutralization reaction equation. So hydrogen ion plus HNO2 equals, okay, so complete reaction. So you're going to produce our conjugate base again plus H2O liquid. Okay, so it's just simple. If we are reacting our hydroxide ion with our base, that means we're going to produce the other one, which is our acid. So basically, it will just involve these two buffer components. So that's why you need to remember. Identify first what is your buffer component. Okay, so since we are using our weak acid, so the concentrations of our weak acid will decrease. Okay, whereas the concentrations of our conjugate base on NO2 negative will increase. Okay, however, okay, this will not change the pH of our buffer system very much because, okay, the NO2 minus concentration that increase will push the equilibrium between the hydrolysis equation of our weak acid to the left. So thus resulting in we reproducing again our weak acid. Okay, so our weak acid concentration will continue to will not increase, but it will remain. Okay, we use it and now we're reproducing again by shifting the chemical equilibrium from right to left. Alright? Okay. So this chemical equilibrium will be shift because of the higher increasing concentration of my NO2 minus. So it will shift from right to left. Okay. So reproducing the use up HNO2, our nitrous acid, resulting in the pH of the buffer system to not changes very much. Okay, so now we are done with the acidic buffer. I've shown you two different examples on how to explain how does the acidic buffer system works to maintain its pH. So let's now focusing on the second types of buffer, which is your okay, so now is your basic buffer solution. So a basic buffer solution will have pH more than 7 because it's basic, and since it's basic, it's going to made up from a weak base with a salts of its conjugate acid. Okay, so we're going to discuss on the examples which I made buffer systems by mixing ammonia as well as ammonium chloride. Okay, if you write down the chemical equation between these two, which is the hydrolysis equation of your weak base in water. So hydrolysis of your weak base is a reversible reaction, okay, which is partially dissociates in water. So this hydrolysis of your ammonia will yield NH4+, which is our ammonium ion, and this one act as a conjugate acid. Okay, so let's check either hydrolysis of my ammonium chloride will yield the same conjugate acid. Yeah, so the hydrolysis of the salts ammonium chloride also yield NH4+ as well as Cl-. So in both hydrolysis equation, we have the same ion produced, which is our conjugate acid, NH4+. Since this combination, this mixture contain the same common ions, therefore it will work as a buffer solution, a buffer system, and we name it as a basic buffer because it consists of our weak base. Okay? Right, so how does this buffer system works to maintain its pH? Okay, so the first you need to identify what is your buffer component. So my buffer component is my weak base and its conjugate acid. If it's acidic buffer, we have weak acid and its conjugate base. If it's basic buffer, it's weak base with its conjugate opposite component. So one must be base, one must be acid. So that's how they're going to maintain the pH by one of the component, which is your acidic component, will neutralize the added OH minus, whereas your base will be neutralizing your added acid. Okay, so let's now label. So our ammonia, which is our weak base, so it will neutralize any added acid. So acid contains H3O+. Okay, whereas our conjugate acid, it will neutralize any added base. So base contain OH negative. Okay. So when I add small amount of strong acid which contains H3O+, so it will neutralize by my base, which is NH3. So let's write down the equation, neutralization equation between our ammonia with the added H3O+. Okay, so since we use up ammonia, that means we're going to produce our ammonium ion, and H4+ equals, and definitely eliminate water because it's neutralization reaction. Okay, so from the neutralization reaction between our ammonia and the added strong acid, so it reacts with H3O+, we're going to produce more of our NH4+. So our NH4+, our conjugate acid concentration will increase, but our weak base concentration will decrease. However, even though it's like that, okay, the NH4+ is quite a strong conjugate acid, so it will push the chemical equilibrium for this hydrolysis equation of ammonia in water from right to left. So increasing concentration of NH4+ will push the position of equilibrium from right to left. Therefore, we are reproducing our used up ammonia. As a result, at the end, there will be no changes or small changes of concentrations of ammonia in the system. Therefore, the pH of the buffer does not change very much. Okay. Alright, so what happened when I add a strong base? So a strong base, that means it will be neutralized by the opposite component, which is my conjugate acid. So let's write down the neutralization equation between the conjugate acid with the added base. So you're going to produce, since I use my conjugate acid, that means I'm going to reproduce my ammonia plus water. Why water? Because this one is a neutralization equation. So all neutralization equation will produce water somehow. Okay, so I'm producing more of my ammonia, so my concentrations of ammonia should be increasing. Okay, however, this ammonia is a very weak base which hardly dissociates again in water to produce hydroxide ions. Therefore, the pH of your buffer does not change very much. Okay, so let's write down our hydrolysis equation of my weak base in the water, which is a reversible reaction because it's a weak base and it partially dissociates in water. Okay, so ammonia is a very weak base, so hardly it is going to push the chemical equilibrium from left to right to produce more hydroxide ions. That's why in these examples, the pH does not change very much. Now, let's do another example. Okay, for your basic buffer, which is we are making a mixture of methylamine with methylamine chloride, okay, which is a salts. Okay, so let's find out either these two mixture can make up as a buffer solution. So let's write down first the hydrolysis equation for my weak base, which is CH3NH2 equals in water. So weak base, therefore it will partially dissociate in water, so reversible reaction, so producing our conjugate acid. So NH2 add another 1 H with plus charge, okay, and releasing hydroxide ion in the equation. Whereas my salts, okay, will completely hydrolyze in water, breaking down into this component ion, which is our conjugate acid, with a chloride ion, which is our anion. Okay, so as you can see in both of the hydrolysis equation, there are common ion present, which is our CH3 and H3 plus. This is our conjugate acid. So the presence of this common ion enables the mixture to work as a buffer system. So how does this basic buffer work? Alright, so let's learn now how does this basic buffer, a mixture of my methylamine and its conjugate acid, work to maintain the pH of its buffer. Okay, so first label now, okay, the base that we have will neutralize all the H3O plus added. Okay, H3O plus, whereas our conjugate acid will neutralize our base, which is OH negative. So if we are adding H3O plus, that means it's an acid. It will be neutralized by its opposite component, which is our base. So let's write down the neutralization reaction that happens between our weak base with the addition of acid. Okay, so it's a complete neutralization reaction. It's a complete reaction which going to produce our conjugate acid in the process, okay, plus water as the final product. Okay, as you can see from the neutralization reaction that happened, we are increasing the concentrations of our conjugate acid and we are decreasing the concentrations of our weak base. Okay, so the increasing concentrations of our conjugate acid will push the equilibrium for the hydrolysis of our weak base towards the left. Okay, so from right, it will push to the left. So it will going to reproduce the weak base that we used in the process. Okay, so these are the reversible reaction that takes place. So we have a higher concentrations of our conjugate acid. Therefore, this higher concentration, heavier part, will push the positions of equilibrium from right to left, resulting in we reproducing again our weak base that has been used up in the neutralization reaction. As a result, okay, no changes in the concentrations of our weak base is taking place. Therefore, the pH of the buffer system does not change very much. Okay, so what happened when I add a strong base? So my strong base, okay, will be neutralized by the conjugate acid that is present. Okay, so it's a complete reaction again. So it's going to produce, since I use up my conjugate acid, so I'm going to produce my weak base in the process plus water as the final product. Okay, so as you can see, we are producing more of our weak base and we are using our conjugate acid. Okay, so the concentration of my weak base will increase. However, this weak base is a very weak base. So therefore, it will not dissociate more in water, or it's very hard to dissociate in water. Thus, no concentrations of OH minus is increasing. Therefore, the pH does not change very much. So let's write down the hydrolysis equation for your weak base as a reference, okay? So it does not push this chemical equilibrium towards the right, okay, towards the right. Therefore, we don't have more OH minus in the systems, okay. As a result, no change in the pH very much. Okay, so we are done with the 2 examples of your basic buffer and 2 examples of acidic buffer. I already explained to you how does this buffer system works together to maintain its pH. Okay, how does the buffer component neutralize the additions of acid and addition of strong base. Okay, you just need to remember, if we are adding acid, that means it's going to be neutralized by the base component that is present. Either it's a conjugate base or the weak base. Whereas if I add a strong base into the systems, into the buffer systems, therefore it will be neutralized by either its conjugate acid or the weak acid that is present. So buffer component must be made up by acid and base that works together. Alright. Okay, so now let's learn how we can calculate the pH of the buffer system. So it's not just simply pH equals to negative log H3O plus concentration, just like when you are calculating the pH of our strong acid or weak acid. Okay, this one is a buffer which is made up of a salts and weak acid or weak base. Therefore, we have a special formula which we name it as Henderson-Hasselbalch equation. Okay, so these are the combinations of Henderson and Hasselbalch, 2 different scientists, okay, Germany if I'm not mistaken. So we have pH if we are using an acidic buffer, okay, and POH if we are having a basic buffer. But from the POH, we can calculate pH by pH equals to 14 minus POH. Okay, so we cannot leave our final answer in the POH. If the question asks you to calculate pH, you need to calculate what is the pH of your buffer. Okay, so let's try now to calculate and using the Henderson-Hasselbalch equation. I have this first example, okay, which I prepare a buffer solution made up of 0.125 moles of sodium nitrite. So this is my salts. Okay, so label it. So this is the N initial. Okay, this 500 milliliter is the volume final, and 0.25 molar is the concentration of my weak acid. And for every buffer systems, if you need to calculate the pH of the buffer, either the buffer itself or after additions of small amount of strong acid or strong base, they will give you the value of the Ka. Okay, so this one is acidic buffer because we are given acid. Therefore, we're going to use the formula pH equals to pKa plus log salt over our weak acid. Okay, so we are given the number of mole of our salts, but we need to have the concentration in order to substitute the value into our Henderson-Hasselbalch equation. Therefore, you have to first calculate what is the concentrations of our salt that being used. So concentration of NaNO2, okay, which is our salt, is simply number of mole divided by volume of the solution, but we need to change it into liter. So this is the molarity formula. So you will get it to be 0.25 molar. Okay, and then you already have the concentration of your salts as well as the concentration of your weak acid, which is also 0.25 molar. Then you can substitute into the Henderson-Hasselbalch equation, okay, plus log salt over acid. Okay, so what is pKa? So pKa is just simply negative log Ka. Okay, so our Ka given is 5.10 times 10 minus 4, okay, and then plus log, our salt concentration is 0.25 and our weak acid concentration is also 0.25. Okay, so if you press your calculator, you will get the pH of the buffer to be 3.29, which is less than 7. Therefore, this one is acidic buffer. Okay, so let's try a different one. Okay, so you were given 0.2 moles of NH4Cl. Okay, so N of your NH4Cl, this is your salt, is 0.2 mole. Okay, whereas our NH4OH, okay, so NH4OH, which is, it has OH, so according to the Arrhenius theory, this is a base. Okay, so 0.10 mole. So now they give you mole and the final volume, which is 1 liter. Therefore, you can calculate what is the concentration of your salts and base. Okay, so they give also the base dissociation constant for your weak base. Okay, so this one, since it's a basic buffer, so you need to calculate using POH first. Okay, but before you substitute all the values into your POH Henderson-Hasselbalch equation, you need to first calculate what is the volume, what is the concentrations of both of your salts and your weak base. Okay, how to calculate the molarity of the concentration? It's just simply number of mole divided by volume. Okay, so NH4Cl, which is 0.20 mole, divided by 1 liter, so I will have 0.2 molar. And for my NH4OH is 0.1 mole divided by 1 liter, so I will get 0.1 molar. Okay, so then you can substitute the value into our Henderson-Hasselbalch equation. Please rewrite first the equation and then you can substitute the value into your equation. Okay, just to remind you, this equation you need to memorize because they will not be given in the exam. Okay, so PKB is exactly the same like PKA, is just negative log KB. So our KB value given is 1.85 times 10 minus 5. Okay, so plus log our concentration of our salts, which is our ammonium chloride, is 0.2 molar over our weak base, which is ammonium hydroxide, is 0.1. So you will get your POH to be 5.03. So pH is 14 minus POH. Okay, so 14 minus POH that you calculated before, which is 5.03. Therefore, the final pH of your buffer system is actually 8.97. Okay? Alright, so let's try a more difficult questions on calculations of the pH of the buffer after addition of small amount of strong acid or strong base. Okay, so from there you can see the changes are very small. So let's try now this example. Okay, so you will prepare, you're going to prepare a buffer solution of containing 0.20 mole of our ethanoic acid with 0.30 mole of sodium ethanoate. Okay, in the question, sometimes they might give you number of mole and the final volume. Sometimes they will give you the concentration, and sometimes they might give you in the form of mass. Okay, so whatever it is, to use your Henderson-Hasselbalch equation, you need to make sure your salt and weak acid or weak base is converted into the concentration. So you need to find out what is the concentration. Okay, so first you have to calculate the pH of the buffer solution. Okay, so let's first now try to calculate what is the pH of the buffer. Okay, so correction. Okay, they give you this in the mole, 0.20 mole as well as 0.30 mole. Okay, so the volume of the solution of the buffer solution is 1.5 liter. That means you need to calculate what is the concentration of both of your weak acid as well as your salts. Okay, so let's calculate first. Your weak acid concentration is just simply 0.20 mole divided by 1.5 liter. So you will get the concentration to be 0.13 molar. Okay, for your CH3COO and A, which is your sodium ethanoate, is 0.30 mole. Okay, divide by 1.5 liters, so you will get 0.20 molar. So now you already have both concentration. Therefore, you can substitute the value into your Henderson-Hasselbalch equation. But before you substitute, please make sure you write down the general formula, okay, as a reference. In case your substitution is wrong, at least they will give you mark for the writing down the correct correct formula for calculating pH of your buffer. So pKa is negative log Ka, and our Ka value for this ethanoic acid is our Ka value for our ethanoic acid is 1.8 times 10 to the power of negative 5 plus log salts concentration, which is 0.20 molar over 0.130 molar. So you will get the pH to be 4.93. It's less than 7, therefore this one is your acidic buffer. So what happened when we are adding small amount of acid? Okay, so they say they're going to add 0.01 mole of HCl. So this HCl is your strong acid, so it contains H3O+, which will be neutralized by CH3COO negative. So let's write down first what is the chemical equation involved. So CH3COO negative equals plus H3O plus equals, so it's complete neutralization reaction producing our CH3COOH plus water. Okay, so then you're going to fill up the ice table. So its first ice tables is in the terms of mole, which is initial mole, changes mole, and equilibrium mole. Okay. So from the question, they give you the initial mole of your salts, which contain your conjugate base is 0.30 mole. So this one comes from the salts number of mole. Okay, H3O plus is the addition, which is 0.01 mole, and ethanoic acid is from the weak acid, which is 0.20 mole. Okay, what is changes? Okay, changes you have to refer to the neutralization reaction equation, in which in the equation I'm using my CH3COO negative. That means I'm going to have the changes to be negative. Okay, so how much is the value? Not in the terms of X, but you have to refer to the number of mole of the added acid or added base. Okay, so we add 0.01 mole of acid. Okay, so the changes for your conjugate base is not in the terms of X, but it depends on how much the added acid is being neutralized. So 0.01 mole of acid is being neutralized, therefore the changes for your conjugate base is also 0.01 mole, and your acid is 0.01 mole negative because we want to remove all the added acid. But since the process produce our weak acid, okay, so therefore this one increasing the number of mole by the same mole of your acid added, strong acid added. So equilibrium mole is just simply initial plus changes, in which this one you will get 0.29 mole, 0 mole for your acid added, and 0.21 mole for your weak acid. Okay, so your focus, you need to make sure there will be no more strong acid or H3O plus or OH minus is present at equilibrium. Okay, after that you're going to calculate what is the equilibrium concentration. So there is no changes in the volume because they just give you the number of mole of strong acid, no volume. Therefore the volume of the solution still remains, which is 1.5 liter. Okay, so equilibrium concentration is just equilibrium mole divided by the final volume, which is 1.5 liter. So if you calculate this one, okay, CH3CO minus, you will get 0.193, 0 for your H3O plus, whereas for your ethanoic acid 0.21 mole, again divide by 1.5 liter, which you will get it to be 0.14 molar. So now you can substitute into your Henderson-Hasselbalch equation to calculate what is the new pH after addition of 0.01 mole of my strong acid. Okay, so pKa again negative log Ka, and our Ka for our ethanoic acid is 1.8 times 10 to the power of negative 5 plus log salts is our conjugate base, which is 0.193 molar, over weak acid, which is our ethanoic acid, 0.14 molar. Okay, so if you calculate your pH, will get be 4.88. Okay, so the original pH is 4.93 without addition of strong acid, but the new pH after addition of 0.01 mole of acid is 4.88. The changes are very small. Okay, so you can consider the pH does not change very much. So what about if I add 0.02 mole of NaOH? So this is a base which contains OH negative. So it will be neutralized by our acid component that is present in our buffer. Okay, first write down the neutralization equation that's taking place so that you can know which one is increasing in concentration, which one is decreasing in concentration. Okay, because it will be related to your ice tables calculation in the next step. Okay, so initially my weak acid I have 0.20 mole, and my ethanoate ion, which is from our salts, which is 0.30 mole. Okay, OH minus added is from NaOH, with 0.02 mole. Okay, so the buffer component that is neutralizing our added base will be decreasing in the number of moles. So how many moles is decreased depending on how many moles of added base. Okay, so we add 0.02 mole of base, so I'm going to remove all the base added. So changes is negative 0.02 for my hydroxide ion, as well as for my ethanoic acid, which is reacting with my hydroxide ion. So negative 0.02, and in my ethanoate ion I'm producing, because the reaction produce our conjugate base, so plus and 0.02 mole as well. Okay, similar number of mole as the hydroxide ion added. Okay, but the magnitude positive or negative depending on either is being produced or being used up. Okay, so equilibrium mole is just simply initial plus changes mole. So this one it becomes 0.18 mole, 0 for my hydroxide ion, and 0.32 mole for my ethanoate ion. So equilibrium concentration is just equilibrium mole divided by volume of the solution, which our volume of solution is 1.5 liter. So 0.18 mole divided by 1.5 liter. So I will get it to be 0.12 molar. Okay, 0 for my hydroxide ion, and for my ethanoate ion is 0.32 mole divided by 1.5 liter. So I will get 0.213 molar. Okay, now you can substitute into your Henderson-Hasselbalch equation. So pH equals to pKa plus log concentration of salts over weak acid, and pKa is just simply negative log Ka value, which ethanoic acid is 1.8 times 10 to the power of negative 5 plus log salts concentration, which is our conjugate base, which is 0.213 molar, over concentration of our weak acid. The new concentration is 0.12 molar. Okay, so you will get the new pH to be 4.99. Okay, if you want to compare again with the initial pH, which is 4.93, still there is no very big change in the pH. Okay, so let's try now with a different example. Okay, alright, so in this time you were given a basic buffer, so they give you the final pH, which is 8.3, but they want you to find out what is the ratio of concentration between the weak base and the salts used up in the buffer component. So first, let's write down pH, and let's first we calculate what is the pOH value. So pH plus pOH equals to 14. Okay, so pOH is simply 14 minus the pH given, which is 8.3, and I will get it to be 5.7. Okay, and then I can substitute into my Henderson-Hasselbalch equation, which is pOH equals to pKb plus log salt over weak base. Okay, in which in our case here our salt is ammonium chloride. Okay, ammonium chloride is our salt and ammonia is our weak base. Okay, so POH that we calculate before is 5.7 equals to the PKB is negative log 1.8 times 10 to the power of negative P plus log our salts is NH4Cl. Okay, and our ammonia is NH3. From here, you're going to rearrange the value. Okay, so if you press 5.7, so this one is going to be positive. So 5.7 plus log 1.8 times 10 to the power of negative 5 equals to log NH4Cl over NH3 concentration. Okay, so I will get it to be 0.955. So this one, everything, it becomes 0.955 equals to log of the concentration of my salts, okay, over concentration of my weak base. Okay, so how I'm going to cancel out the log is just simply 10 to the power of 0.955 equals to NH4Cl concentration over NH3. Okay, and then if you press your calculator, you will get the value to be 9.02, which is around 9, equals to NH4Cl over NH3 concentration. Okay, so it's actually over 1. So the ratio is about 9 to 1. 9 is for my NH4Cl. Okay, and 1 is for my NH3. Okay, that's how you are calculating the ratio. Okay, so let's now try with this next example, which is another basic buffer solution made up of your ammonia with ammonium chloride. So right now, instead of giving moles, they give you the molarity of both of the solution. And the first one, you need to calculate what is the pH of the buffer. Okay, so how do we do this? Okay, so since it's already give you what is the concentration, so we can just simply substitute into the Henderson-Hasselbalch equation. Okay, so POH equals to PKB plus log NH4Cl, or you can simply write down salts over our weak base ammonia. Okay, so PKB is negative log Kb 1.8 times 10 to the power of negative 5 plus log concentration of my ammonium chloride, which is 0.25 over 0.15. Okay, so if you press your calculator, you will get your POH to be 4.97. So pH is simply 14 minus POH, okay, which is 14 minus 4.97, and you will get your pH to be 9.03. Okay, let's now try to calculate the new pH of the buffer solution after addition of 0.02 moles of KOH. So KOH is your strong base. Okay, according to the Arrhenius equation, it has OH in the formula, so it's a strong base. So it will provide you with OH negative. Therefore, this OH negative will be neutralized by the conjugate acid that is present. Okay, so let's write down the chemical equation that is involved. Okay, so from there you know which one is producing and which one is being used up throughout the reaction. Okay, so we're going to use our ammonium ion and we're going to produce our ammonia. They only give you the molarity of your ammonium ion as well as your ammonia and the final volume of the solution, which is 2.5 liter. So that means you need to calculate first the initial moles of your ammonium as well as ammonia. Okay, so how to calculate number of moles is just simply molarity times the volume. So molarity of the ammonia given is 0.15 molar. So multiply by 2.5 liter. So you will get it to be 0.375 mole. Okay, whereas for my ammonium ion, which is our conjugate acid, the molarity is 0.25 molar times with the volume given 2.5 liters, so you will get 0.625 mole of initial mole. Okay, so fill up the ice table with the calculated number of mole. And for the hydroxide ion, it simply comes from our KOH, which is 0.02 mole. Okay, so changes is not in the terms of X, but this one, you have to refer to the number of moles of the hydroxide ion that is present. So we want to remove all the hydroxide ion that is available, so 0.02. Since ammonium ion is reacting with my hydroxide ion, so the changes is negative 0.02. And my ammonia is being produced throughout the reaction, so positive 0.02. 2. Okay, so equilibrium is just simply initial mole plus with the changes mole. So I will get 0.605 for my ammonium ion, 0 for my hydroxide ion, and 0.395 moles for my ammonia. Okay, so at equilibrium, the concentration is simply number of mole at equilibrium divided by the volume of the solution, 2.5 liters. So you will get the ammonium ion to be 0.242 molar, and my ammonia is 0.158 molar. Okay, then now since you already have the concentrations at equilibrium, you can substitute into the Henderson-Hasselbalch equation. Okay, so POH in the terms POH, because we are calculating for basic buffer, so we need to use KB and PKB. So POH first, and then you can calculate pH later on. So PKB is negative log KB, and your KB is 1.8 times 10 minus 5 plus log concentration of your salts, which is 0.242, over concentrations of your ammonia, which is 0.158. Okay, so you will get your POH to be 4.93. So how to get pH? pH is just simply 14 minus POH, and your POH is 4.93, and your new pH is 9.07, which is just a little bit different from the initial pH, which is 9.03. So even though you add KOH into your buffer solution, the changes of the pH is still small. Okay, provided the additions of the strong base is just very little. Okay, so I'm done giving you many examples on how to explain how does the buffer system works to maintain its pH, and a few more examples on how to use Henderson-Hasselbalch equation to calculate the pH of the buffer that initially present and the new pH of the buffer after additions of strong acid or strong base. Okay, so now it's time for you to test yourself to check your understanding. Okay, so this one is in the quiz form. Okay, so this one is just a simple calculation to calculate the pH of your buffer solution, and this one is acidic buffer because the reaction between acetic acid and sodium acetate. So you're just going to use your Henderson-Hasselbalch equation, and you have another one quiz, which is quiz 5, which is more difficult. Okay, because besides you have to calculate the initial pH of your buffer, you also need to calculate the new pH after addition of strong base into the buffer systems, and you need also to explain how does the buffer system works to maintain its pH. Okay, so make sure to try to answer quiz 4 and quiz 5. We're going to discuss about it in our week 17's tutorial. Thank you for watching for your buffer solution movie. I'm going to see you guys again in my next movie, which is on about titration. Bye bye.